Welcome to another unit in the ISM Exercise Set Statistics 2, this time with a unit on the coefficient of determination and the F-test. Let's have a look at the exercise. The relation between the age of a car and the yearly repair costs should be analyzed. For this, the following first data set has been collected. And here we get for 5 different cars the age and the repair costs. And A, using the method of ordinary least squares, estimate a line that describes the relation between the two variables. And B, calculate corresponding coefficient of determination and interpret it. And finally C, use a suitable test to test whether the calculated relation is significant at the 5% level. So let's start with the regression line. For this, we copy our table. We know x is the independent, the repair costs are the dependent variable. So we extend our table by the squares of the age and by x times y, so age times repair costs. In addition to this, we also calculate the average of all of the 4 data series. Because when we want to calculate the regression line, we only need those 4 last values. Because here, the slope parameter b is given as the average of x times y, so the 904, minus, then we have the average of x times the average of y, so here 7 times 94. And all of this is divided by the average of x squared, that's 62.6, minus the average of x squared, so 7 times 7. So here we get a slope parameter of 18.0882. With this slope parameter and the averages of x and y, we can calculate our intercept. So here the intercept is average of y, so 94, minus the b we got from above, times the average of x, which is 7. So here we get an intercept of 32.6174, giving us in total the following regression line. Well, what does the regression line signify? We cannot say any sensible thing about the intercept, but the slope would mean for every year that my car gets older, the repair costs will increase by roughly 18.09 euros. Okay, so much for part A, for the regression line. Now we want to get the coefficient of determination. For this we copy the regression line. And if we want to calculate this, we also need the table. And we need to extend the table, first off for y squared and for y hat squared. We could do a different approach here. Because we only have one independent variable, we could also calculate the correlation coefficient of Pearson and then square this. This works, however, this only works if we have one independent variable. So here, what we're going to do instead is calculating y hat squared. Y hat, that's the value we get when we insert x into the regression line. So for the first one, we calculate 18.0882 times 2 minus 32.6174, giving us here 12.67. The same thing we're going to do for the other different values here. And always the result we get is squared. Okay, so much for this. And then, again, we take the averages of all 4 values. Because again, that's what we are interested in. Because r squared then is determined as here, as we can see it, the average of y hat squared, so the 13,285.69, minus the average of y squared, so minus 94 squared. And all of this is divided by the average of y squared, so 13,620, again minus the average of y squared, so minus 94 squared. So this results, in this case, in an R-squared of 0.9301. Okay, this gives us the coefficient of determination. And if we have this, we can also perform our F-test. That's, well, part 3. However, before this, we were asked, what does the 0.9301 actually mean? This means that our regression line, the one we determined in A, can explain 93.01% of the variance of the dependent variable, so of the repair costs. The F-test we're going to perform next tests whether this is actually a significantly enough share, large enough share, so that we can say a significant part of the variance is explained via the regression line. So next step, that's the F-test. So here we're going to calculate the F-statistic. The test statistic first, and this is given as R-squared divided by K, K being the number of independent variables, so here it's only 1, divided by 1 minus R-squared, divided by n minus K minus 1. N is here the number of observations, so in this case 5. So we get here 5 minus 1, so here we have 3. So in total, this results into a test statistic of 39.9185. Then, in addition to the test statistic, we also need a reference statistic. The reference statistic of the F-test is always given as F, K, n minus K minus 1, and 1 minus alpha. Okay, we said already, K is 1, n is 5, and from the exercise text, we get an alpha, an acceptable error of 5%. So if we insert all of this, we see we need the F value for 130.95. So we look up this value in our table of the F distribution. There we find a value of 10.128. Now we're comparing this value to the test statistic. Then we see that here our test statistic is larger than the reference statistic. So in this case, we can reject our H0 hypothesis. And H0 hypothesis here in this case of the F-test means model has no explanatory power. So if we can reject this, we know our model has significant explanatory power. Okay, this then finally concludes this exercise, which I hope you enjoyed. And if you want to see more exercises, feel free to visit the rest of the exercise set or have a look at the corresponding playlist. I say goodbye and see you next time.